Dear students, today we will discuss Orested experiment from Unit 3, Electromagnetism. Orested was a scientist who concluded that a magnetic field is always associated with a current carrying wire. When a magnetic compass needle is placed near a current carrying wire, then it gives deflection. In the figure you can see that as the key is on, when the key is on, here the key is on. When the key is on, the current is flowing through the circuit. When the key is on, the current is flowing through the circuit. And when we place a magnetic compass needle near this circuit, then the compass needle shows deflection. In the second experiment, in the second figure, we can see that the poles of the batteries are reversed. The poles of the batteries are reversed. In the first diagram, we can see that we have placed positive pole on the left hand side and negative pole on the right hand side. But in the second diagram, we can see that first pole is negative terminal and second one is positive terminal. That is, when we interchange the poles of the cell, in that case the direction of current in the circuit changes. In the circuit we show conventional direction of current, that is from positive to negative. The current is going from positive terminal to negative terminal. Similarly, in the second circuit, current is also going from positive to negative terminal. And when a magnetic compass needle is placed near these circuits, then it shows deflection. With the change in the direction of current, the direction of deflection of magnetic compass needle also changes. In the diagram, it is clearly shown that when the direction of current changes, then the magnetic compass needle also reverses its direction of deflection. We can explain it better by using Ampere swimming rule. Ampere swimming rule. It states that imagine a man swimming in the direction of current such that current enters from its feet and leaves through its head. Ampere states that consider a man swimming in the direction of current such that current enters through his feet and leaves through his head. Then the north pole of the magnetic compass needle will deflect towards the left hand of the swimming man. The north pole of the magnetic compass needle will deflect towards the left hand of the swimming man. Similarly, in the second diagram, imagine a swimmer swimming in the direction of current. Understand it properly. That man is swimming in the direction of current such that current enters through his legs and leaves through his head. करंट उसके लेग्स में एंटर करते हुए उसके हेड वाले पार्ट से क्या कर रहा है, लिव कर रहा है, बाहर की तरफ जा रहा है. इन दैट केस द डायरेक्शन ऑफ मैग्नेटिक कंपास नीडल इज again the same. The north pole of the magnetic compass needle will show deflection towards the left hand of the swimmer. I hope you understand this topic well. Thank you. Dear students, in this video, we will cover the next topic from Unit 3, Electromagnetism. The topic is magnetic field at the center of a circular coil carrying current. In this topic, try to understand the diagram first. In the given diagram, we have taken a coil, a circular coil, in which the current is flowing in the clockwise direction. In the diagram, the current is flowing in the clockwise direction. The radius of the circle is taken as r. we have taken a small current element of length dl from the circular coil. कंप्लीट सर्कुलर कॉइल में से हमने अपनी तरफ से एक छोटा सा करंट एलिमेंट ले लिया, यानी वायर का एक छोटा सा पीस हमने कंसिडर किया है जिसकी लेंथ हमने ले ली dl. dl is making an angle of 90 degree with a radius r. The angle between dl and r is 90 degree. Now using Biot-Savart's law, the magnetic field at the center due to the small current element dl is given by dB is equal to mu naught upon 4 pi I dl sin theta upon r square. This is the center of the circle. This is considered as point O. This is the point O. And at this point O, the magnetic field induction is given by Biot-Savart's law, that is dB is equal to mu naught upon 4 pi I dl sin theta upon r square. Now as we discussed that the angle between dl and r is 90 degree, so we put theta as 90 degree. Sin 90 is 1. So we will get dB is equal to mu naught upon 4 pi I dl sin 90 upon r square. Now in the derivation, we get dB is equal to mu naught upon 4 pi I dl upon r square, as sin 90 is 1. Sin 90 is 1. That's why this disappears from the expression and we get dB is equal to mu naught upon 4 pi I dl upon r square. Now the total magnetic field at the center at the point O due to the whole circular coil current. dB is the small amount of magnetic field constituted at the center of the circular coil due to the small current element of length dl. Now we have to find out the total magnetic field due to the whole circular coil. So we have to integrate the expression. On integrating the expression, we get the integration of dB is b. We get b is equal to, in right hand side, see it clearly that we have to integrate the expression with respect to dl. So इंटीग्रेशन के अंदर हम सिर्फ dl को रखेंगे, बाकी जो सारी टर्म्स हैं दे विल एक्ट एज अ कांस्टेंट, उन्हें हम इंटीग्रेशन के साइन से बाहर ले लेंगे. नाउ इन द नेक्स्ट स्टेप वी हैव टू इंटीग्रेट dl. dl is the small current element of the circular coil. The small current element of the circular coil is dl. This length is considered as dl. And now integrating dl, we get the complete length of the circle, and the length of the circle is its circumference. So on integrating dl, we get 2 pi r. I will cancel out this power r square, and we will get as b is equal to mu naught upon 4 pi 2 pi I upon r. The value of mu naught upon 4 pi is 10 raised to power minus 7. So in the numericals, we will directly substitute the value of mu naught upon 4 pi as 10 raised to the power minus 7. And if the circular coil has n number of turns, the result will be b is equal to mu naught upon 4 pi 2 pi in upon r. We will not cancel out pi from pi, just for the sake of simplicity, that we can substitute the value of mu naught upon 4 pi as 10 raised to the power minus 7 directly in the numericals. So we have to learn this result, that b is equal to mu naught upon 4 pi 2 pi in upon r. Thank you.